We're over the high mountains and wide valleys that lie between Colorado's Rocky Mountains and Washington's Cascade Range. Precipitation through this region is precious, maybe 20 or 30 inches a year in the high country, but not even 10 inches in some of the low spots. Drought, with its long winters of little snow, is an ominous word to people who try to make a living here. To get started, let's look through the eyes of a physical geographer who's worked extensively in the Intermountain West. Erica Wise is fascinated by climate and storm patterns. Back home in North Carolina, she teaches courses on physical geography and climate change. Out here, she drills tree ring cores from ponderosa pines and Douglas fir. The cores reveal annual growth rings, some thick, some thin, that tell of dry and wet years. On this trip, she's working with Dannenberg, who's modeling forest growth in times of climate stress. Tall tree height is often an indicator of rapid rather than sustained growth. Erica looks for old trees with unbroken records of past climate. Old pines tend to have raggedy flattened tops and smooth bark. They might have scars from fires in the past. Erica usually heads uphill to weather-beaten ridges where the trees have pronounced thick and thin growth rings that make the interpretation of past climates more obvious. The oldest ponderosas she's found so far started growing in the year 1390, more than 600 years ago. A lot of people still remember the dry, Dust Bowl years of the 1930s. Farms collapsed, animals died, ranchers gave up. But after a few generations, memories and written history begin to blur. Where can scientists find a longer view of this region's environment? The study of tree rings, called dendrochronology, is a tool that geographers have employed since the 1800s to reconstruct past climates. The Dust Bowl drought is faithfully recorded in trees that lived through the 1930s. But Erica Wise's cores reveal wet and dry periods that stretch over 6 centuries. Remember, in the West, forests and people have always depended on a steady supply of rain and snow. Armed with tree ring data, geographers can offer a knowledge of past climate patterns that are useful to anyone who wants to know what the future might hold. Sounds straightforward, doesn't it? Drill a core, count the rings, and publish the results. The story gets a little more complicated, though, when you start correlating different trees from different locations. Wise and Dannenberg are measuring oxygen and carbon atoms within individual growth rings. Erica is trying to show how stable isotope concentrations reflect the distance and direction that a storm travels inland. After cross-checking this data against similar isotope concentrations in soil water, Erica plots information from old trees scattered around central Washington. Modern-day storms follow different paths depending on regional pressure patterns out over the Pacific Ocean and the Aleutian Islands. Erica is trying to reconstruct not just past climates, but past storm tracks, something that nobody has done before in this region. Her research takes us one step closer to understanding why and how climates fluctuate over long periods of time, in the past and perhaps in the future. Physical geographers can use dendrochronology, or the analysis of tree rings, to help determine the species of a given tree, changes in climate and annual rainfall that occurred in a tree's lifetime, the density of vegetation in different regions. In areas where climates are relatively predictable, tree rings can be used to determine both short and long-term changes in climate and other environmental conditions. Who said geographers just look at maps? We try to understand our role within a landscape. Why is what where? It's imperative to know how that landscape fits together in the first place, how rock becomes soil, where water flows, why plants grow here rather than there. Physical geographers ask how and why landscapes have changed over time. They study why slopes fail and how valleys fill with sediment. They model the immediate influence of weather and the long-term effects of climate. Geographers also want to know what we're doing to our planet, and what can be done to protect it in the future. Back home, Dannenberg spends plenty of time tethered to a computer, but he believes that geography students need to get out into the real world, to hike, to see, to get their hands dirty, to make a difference. Erica Wise would like to prepare them to tackle one question that she feels is terribly important. How are we humans interwoven into the fabric of our landscape? Matt Dannenberg is right. It's good to step away from the computer and come up for air once in a while. These field trips are meant to pique your interest in some of the subjects that physical geographers study. They'll try to bring you face to face with intriguing landscapes. But the field trips are still electronic, still a virtual experience. We hope you'll learn what you can from them, and then have the chance to head out into the real world, on your own, as a geographer.